P of box initial square equals mass 1/2 mass of rod speed of rod final squared plus 1/2 mass of box speed of box squared. All right, so that's what we're working with. Those are the basically conservation of momentum, conservation of kinetic energy. Let's just go ahead and plug and chug, and I'm going to go ahead and I'm going to set this equal to C and this equal to D just to avoid having to write subscripts. All right, so I have 1 times 58.5279 plus 2.4 times 0 equals 1C plus 2.4D. The second equation, I'm just going to go ahead and multiply by half to get rid of those. Or, sorry, multiply by 2 to get rid of all the 1/2s. And so I have 1 times 58.5279 squared plus 2.4 times 0 squared equals 1 times 1C squared plus 2.4D squared. I'll go ahead and do the left-hand sides. Or I'll do actually the first one. So we have 58.5279 equals C plus 2.4D. The second one, yeah, I cannot do that one in my head. Other than it's something less than 3,600.
527.
To 58.527, it's this number right here.
I see. $3,425.
3,425
Yes. 0.515.
equals C squared plus 2.4 D squared. All right, 2 equations, 2 unknowns. Probably simplest to solve for C, plug in. So from the first equation, C equals 58.5279 minus 2.4D. Plug that in there, and we are left with, I got 3,425.515 equals 58.5279 minus 2.4D squared plus 2.4D squared. Now what?
Get it in proper form.
All right, so I have 3,425.515 equals, well, that's squared, which is 3,425.515 minus twice the product of those. So whatever that is. So it's 2 times 2.4 times 58.5279.
So 2 times what's in the parentheses?
2 times that times that.
I see. 176.
2.4 squared.
It is.
First one I just was multiplying the wrong things.
Alright, so 2 times 58.5279 times 2.4.
Okay. I did 2 times both of them.
Ah,
I just added them together.
okay, that would definitely mess it up.
Negative 282.10.
282.10.
Right. 45 after that.
282.45.
1045.
1045. What?
You press one of the buttons at the bottom left, like your elbow or something.
What does that do? Toggles back and forth between something. 0.1045D. Conveniently, my constant term is going to drop out. So I am left with, nice to be able to see that while I'm writing stuff down. So I have 0 equals, let's see, the d squared term, we got 5.76 plus 2.4, 8.1, 8.16. Well, if it's wrong, we'll know in a moment. Minus 282.1045D. You can use plus 0. You can use quadratic formula if you want to. Or we can just factor this. So 0 is equal to d times 8.16d minus 282.1045. So d equals 0, the non-collision solution, or that's equal to 0. So d equals 282.1045 divided by 8.16.
.572
Units?
meters per second.
Yes. And then we could extend it more by having the mass then go along the frictionless surface and then go down a hill, so we've got a conservation of energy problem. Glide into a spring, another conservation of energy problem.
On its way back up, someone put some chewing gum on it so there's friction.
That is possible too. I think in the original, this is a variation of a problem I did. If you look at old tests and you see something labeled, this is the Rube Goldberg test, this is based on that. This is most of the Rube Goldberg test, at least the beginning of it. I also had it rotating. I actually had a ball spinning in there, hitting the mass, rolling down the incline. Yeah, I think the incline. All right, questions? Because they did promise the ladder problem. Just got carried away on this one. Then let's do the ladder problem. wall is frictionless. The ground is not. It is not a ramp, it is a ladder, so there's gonna be various rungs on here. Let's put this at an angle of, let's make it 50 degrees. I need a mass here. Mass of the ladder, put at 10 kilograms. There'll be a person standing on the ladder. Mass of person, we'll put it at 60 kilograms. And on the ground, u sub s is equal to 0.4. And what I want to know is, how far up does the ladder can the person go before the ladder slips? So we will start out the way we've started out so many problems. The way you solve these problems in your dreams, probably start with the force diagram. So person is, that's some distance x. All right, what are the forces acting on the ladder? We assume a uniform distribution, so the weight's acting in the middle. Oh, I do need to give a length here. Why don't we make that 20 meters long? So 10 meters up, the weight's acting downwards. Sorry, that's one of the questions of where. In the middle. Or what else?
Friction on the bottom
Acting which way?
to the right on the ladder.
Okay. We've got at least 3 more.
Normal force is the person on top of the ladder.
Yep. Acting somewhere, we don't know exactly where, it's some distance x from the bottom, so I'm just gonna put it where I've got some space here. So this is the normal force from the person. So if we're gonna label that normal force from the person, we'll need to do a force diagram of the person also. Properly, we should have, anyway. So we've got 2 more forces on the ladder, 1 more force on the person.
Weight person. Would it be normal force where the ladder is hitting the wall,
Yep, going which way?
away from the wall?
I'll call that y sub h for horizontal. 1 more.
There's friction on the ground going to the left.
On the ground, yeah. We're going to the ground. But, all right. Friction, then I've got weight of ladder, let's go ahead and label that, and then weight of.
No more force
Where?
up on the ladder.
Yeah, because it's touching the ground also. I can't have, if there's friction, there's gotta be a normal force. So y sub v. All right. Let's get the linear equations of motion. And then we'll tackle the rotational one. Now, as far as the person walking up, if the person is running up the ladder, which is a foolish thing to do, then the normal force will often exceed the weight when he's pushing up and when he lands. So let's assume that he is walking up as carefully as possible so that the normal force acting up on the person and his weight are about the same. So he's walking up so incredibly slowly that we're working with that normal force is approximately equal to the weight.
Will they cancel each other out with the force equation?
No, what it does is it allows us to set that equal to the weight of the person. All right, so what are our equations?
The normal force needs to be added on the ground.
Normal force that we added on the ground.
But on the diagram.
All right.
Y sub V.
Y sub V.
No, like on the diagram, Y sub V is not there.
Oh, down here.
Yeah.
Ah, got it. I'm with you.
We're getting equations for all three objects, right? For things.
If you recognize this, which means that that's equal to the weight of the person, then I'll just have three equations with the ladder. I won't have,
Oh,
if you did it for the person, we'd end up with this. The ground, I don't care about. Other than it just performs the service of keeping the ladder up. So what are the linear equations for the ladder? Apparently Dominic, unknowingly, or my interpretation unknowingly, started this off.
Y sub V minus W sub L minus W sub P is equal to MA, or N.
Or just M.
There's no acceleration.
Therefore,
It's just N, it's 0.
0.
Well, N times 0.
Okay, I'll buy it. Yeah, we are trying to figure out, so we're trying to figure out where the person needs to stand in order for the ladder to slip. What we're really solving for is the last place he gets to before it doesn't, when it doesn't slip. And so if he just goes just a little bit more, it will slip. All right, so we got one equation there. Another equation? A horizontal equation? And recognize that Dominic set up as positive. Let's go ahead and make that J hat.
What about,
Which way do you want to make positive?
that's the right?
Okay. So that sets K hat to be positive outside. Again, assuming a right-handed coordinate system. So this is our J hat equation here. So what is the I hat equation?
F equals Y horizontal.
I'm gonna go ahead and put it into the more traditional form to start out with, but yeah, it breaks down into F equals Y horizontal. And now the K hat equation. This is very similar to the problem that we did on Monday, except for the fact that it's up at an angle. But it is in static equilibrium, we hope. So since it is just sitting there, it is not moving at all, there's no rotation, there's no translational motion, we have to figure out where the axis of symmetry, or axis of rotation is. As established on Monday, any place works. However, it is recommended that you pick a place that will eliminate as many unknowns as possible. Weight of ladder, weight of person, those are simple enough to find. mg, I gave you the mass, all I need to do is identify the planet. Where would be a place that would eliminate two unknowns?
The bottom.
Okay. I assume the bottom of the ladder.
That won't work there.
So if we pick that, then these exert no torque. What is another location we can pick that will eliminate 2 torques?
I guess the person,
Where?
the person, or are we just going with ladder?
If we did the person, so eliminated this, that's gonna only eliminate 1 torque.
The middle,
That will eliminate 1 torque.
oh, I didn't know the weight was gonna be in the middle. Oh, so,
You trailed off there. You didn't know,
I didn't know the weight was in the, like, in the direct middle.
oh, yes,
Yeah,
we are assuming the uniform ladder.
what do you mean, in the middle of weight of ladder and weight of, weight of ladder and no more force of person in the middle?
Oh, right there?
Yeah,
That would eliminate no torques.
oh, yeah.
Right.
I mean, where the,
That would eliminate 1 torque.
where the person, the ladder meet.
Right here. That would eliminate 1. So this will eliminate 2. I think that, hopefully you can see why that eliminates 2. There eliminates 1, there eliminates 1, there eliminates 1. But there are other locations that will eliminate 2. If you will recall, the location for something that is just sitting right there for the axis of rotation is whatever's convenient. Another place which will eliminate 2 torques is here. I could, this also potentially, if we want to consider that an unknown, that will eliminate those 2 torques. That will eliminate those 2 torques. But the 2 options, I think, eliminate, the simplest ones are those 2 right there.